So class, let's talk about fatty acids. This will represent a brief review on fatty acids. This is a molecule that belongs to a large umbrella term known as lipids. So lipids don't all look alike. So you can have cholesterol, you can have testosterone, you can have vitamin A, vitamin C, vitamin D. You could have your phospholipids, which contain as a component fatty acids. So this lipids is really a catch-all umbrella term. So steroids such as cholesterol or testosterone are steroids, which are lipids, but they look very different than phospholipids, which in turn look very different than fatty acids. So fatty acid is our simplest molecule that we will study in terms of this umbrella term lipid. So fatty acids would be the simplest type of lipid. One thing that sort of unifies lipids together, whether it's your vitamins, your steroids, your fatty acids, and your phospholipids, one thing that unifies this is that most lipids are soluble in organic solvent, like your chloroform, like your methanol, anything that's organic, the typical solvents that you've studied in organic chemistry, lipids tend to go into them. Okay. Speaking of lipids, there's also the leukotrienes, the prostaglandins involved in pain perception. That class of molecule also is a lipid. So very diverse. All of them are categorized by the one similarity is that they like to be in solution if that solvent is an organic solvent. You'll never see lipids soluble in water. Okay, very, if that exists at all, I don't know. Probably non-existent, but lipids are mostly soluble in organic solvents. So the simplest lipid are fatty acids, and these are long-chain carboxylic acids. Okay, so what is a carboxylic acid? Okay, that functional group is RCOOH or RC double bond OOH. That R group is going to be a long chain alkyl group for these fatty acids. So CH2, 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 and then you end it with a terminal methyl group. All right. So that's what a fatty acid is. Okay. So the complexity comes when you try to name these fatty acids. When you try to name these fatty acids, typically you have a denotion. Okay? Now, the fatty acid long chain, this chain which will represent the R group, can be anywhere from 20 carbons to 16 carbons to 14 carbons. It could even be 1 carbon. All right? So this is technically not a lipid, but if R is H, what do you have here? Okay, you have formic acid, okay, which is not a lipid. It really depends on how you define it, but biologically speaking, you won't see formic acid in our membranes, and you won't see formic acid as a fatty acid in the biological sense. Maybe you'll see formic acid in metabolism, but fatty acids generally are going to be long chain. Okay, this R group is going to be a long alkyl group. And but by the way, fatty acids are found in our body. Our body can use them as a source of energy, but fatty acids are a component of lipids, phospholipids, the membrane. So in biology class, you may have drawn a phospholipid in your phospholipid bilayer. Okay, remember our cell membranes are a bilayer, also the membranes of organelles. So that long little tail is actually going to comprise of a fatty acid. Okay, so this region is the fatty acid. Okay, and you probably recognize this circle as the phospholipid head group, or the phosphate head group more specifically. Okay, so you can have variations here. Okay, the head group can be many different things, but this fatty acid can also be many different things. And what I've shown here are And like that, you're going to have 2 fatty acids, right, per phosphate head group. But this fatty acid, this long chain region, exists in many different forms. And what I've shown here are 5 different forms of fatty acids and the way we denote them. So let's just understand how we work through this symbol, or the symbolism here. Okay, the first number actually represents the number of carbons. And then we have a colon, and to the right of that colon is another number, and that actually tells us the number of double bonds, okay, in that long chain alkyl group, number of double bonds. All right. So if this R group has 16 carbons, then you have your carboxylic acid, then that is a 16N0 molecule. Fatty acid. It also has the name of palmitic acid. Okay. If you have an 18 carbon fatty acid with a 1 double bond, and we designate what carbon that double bond is in. So this would be at carbon number 9, but this is tricky. Okay, it's tricky because where do we count it? Where do we count it? Do we count it at from this carbon, from this end, going this way? Or do we count it from the R group going that way? Okay, so if we count it from the terminal methyl group, then we designate that carbon that contains the double bond as omega. If we count it from the carboxylic acid going that way to the left, then the carbon that has the double bond will be delta. All right, so let's just draw the structure of these 2 fatty acids. By the way, 18N1 double bond with a double bond at carbon number 9 is oleic acid. Let's draw these. So palmitic acid should be easy to draw. So that is 16 carbons, a 16 carbon carboxylic acid. Okay, so this is what it would look like. CH3, that's carbon number 1, CH2, CH2, 1, 2, 3, 4, 5, 6, 7, 8. I have to zoom out here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That is my carboxylic acid at the end, COOH. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. The 16th carbon represents my COOH. So that's palmitic acid. Very easy. Okay. You notice here there is no double bonds. No double bonds in this fatty acid. Okay. No double bonds. So we call something that has no double bonds a saturated fatty acid. That is to say, saturated with hydrogens. Okay, saturated fatty acids. So let's draw oleic acid. Okay, what did we say this symbol represents? Okay, 18 carbons, 1 double bond. Where does that double bond come from? It comes from carbon 9, or it comes at carbon 9. Okay, so either we can count those carbons from the terminal methyl group. If we do, then that double bond designation will be terminal, will be from the terminal methyl group. Or if we count it from the carboxylic acid carbon, then we give that carbon atom that has the double bond as delta. So let's draw the structure of oleic acid. 18 carbons, 1 double bond, and I'll count it from the carboxylic acid end. So it will be delta 9, okay, counting from the carboxylic acid end. So we have 18 carbons, so let us go here. We'll count this COOH as 1, carbon 1, 2, 3, 4, 5, 6, 7, 8, 9. That's where the double bond is going to be, counting from the carboxylic acid end. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that double bond is at carbon number 9. Here's carbon 10, 11, 12, 13, 14, 15, 16, 17, and 18. All right, so here's 10, carbon 11, carbon 12, carbon 13, carbon 14, carbon 15, carbon 16, carbon 17, carbon 18. Okay, here is my double bond. That is the structure of 18,1 delta 9, because counting from the carboxylic acid end, the double bond is at carbon 9. Okay, what about at the omega end? Okay, at the omega end, this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, carbon 7, carbon 8, carbon 9, carbon 10, carbon 11, carbon 12, carbon 13, carbon 14, carbon 15, carbon 16, carbon 17, carbon 18. So really, you know, whether you count it from the terminal methyl group or if you count it from the terminal carboxylic acid group, you're still going to get the same double bond occurring at carbon number 9. So 18,1 delta 9 counting from the terminal carboxylic acid, 18,1 omega 9 counting from the terminal methyl group. All right, I'm not going to go into drawing all of these structures. Maybe I'll draw one more. I don't think I can fit 20 carbons on a piece of paper. But how about we draw 18 and 3, okay, at double bonds 9, 12, 15, 3 double bonds at carbon 9, carbon 12, and carbon 15. So let's see if we can do that. This molecule, 18,3 with 3 double bonds, is actually called linolenic acid, or let's just complete this. 18 with 2 double bonds at carbons 9 and 12 is actually called linoleic acid, and then 20 carbons with 4 double bonds at positions 5, 8, 11, and 14 in the acyl chain. Also, acyl chain is another thing we'll call this the R group long chain fatty acid, is also known as the acyl chain, that long end. 20 carbons with 4 double bonds at carbons 5, 8, 11, and 14 in the fatty acyl chain is known as arachidonic acid. Arachidonic acid. This is actually a precursor to the leukotrienes and prostaglandins, which are involved in pain perception. So your body takes this 20 carbon fatty acid and makes other stuff with it that are actually, these are the arachidonic acid makes the leukotrienes, and which is a very local hormone. It's a hormone that's produced and acts in very nearby tissues, but the precursor comes from, or your body makes that from, this 20 carbon fatty acid, polyunsaturated, 4 double bonds. All right, so speaking of saturation, all right, palmitic acid, 16 carbon fatty acid. Here's our methyl, here's our carboxylic acid, that's saturated with carbons. Contrast that with oleic acid. We have 1 double bond, so that is an unsaturated fatty acid. I can even go so far and say that it is a monounsaturated fatty acid because it has one unsaturation point. So it's a monounsaturated fatty acid. So let's draw one more here. How about we draw the 18,3 fatty acid? So linolenic acid, so that is 18 carbons with 3 double bonds, and they are at positions 9, 12, and 15. So 9, 12, and 15. And let's just draw it. Okay, let's draw it either in the delta form or in the omega form, omega fatty acid form. Okay, so this would be a polyunsaturated fatty acid. Okay, or triunsaturated fatty acid, but we'll just call it a polyunsaturated fatty acid. 18 and 3 double bonds at carbon number 9, 12, and 15. We call this linolenic acid. So let's draw this here. Okay, it either can be in the delta form, or if we're counting from the carboxylic acid end, or the omega form. Okay, so let's count this. 18 carbons, 3 fatty acids. All right, so here is carbon 1, carbon 2, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we got 9. So here's 12, 13, 10, 11, 12, 13, 14, 15, 16, 17, 18. So let's count these carbons again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So this would be 18, 3, and since I'm counting from the carboxylic acid end, it will be delta N, comma, delta 12, comma, delta. So this is one way of depicting the fatty acid, linolenic acid. Let's count from the terminal methyl group, the omega end. So 18 carbons. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I have 18, 3 double bonds as before, but they are at positions omega 3, omega 6, and omega 9. Okay, this is also how we can state the structure as linolenic acid. So linolenic acid is what we will call a polyunsaturated fatty acid. Okay, if oleic acid is a monounsaturated fatty acid, this would be a polyunsaturated fatty acid. So this is how we would draw that structure. So a little bit of a word now on how these things would interact with one another. All right, so how would they interact with each other? How would linolenic acid interact with palmitic acid, which in turn would interact with arachidonic acid, which in turn can interact with all the other different types of fatty acids. Okay, so in these two molecules, actually, the acyl chains would interact. Okay, the acyl chains would interact, and because they're hydrophobic, and the carboxylic acid ends would interact because they're polar. Those two functional groups are polar. All right, so fatty acids are actually what we would call amphipathic, because they'd have a polar end and a nonpolar end. Possesses both a polar and nonpolar attributes. Okay, so the polar attributes, I want you to imagine these fatty acids are interacting with one another. These polar attributes would be from the carboxylic acid end, and the nonpolar attributes would be from the what I would call, or what is called, the fatty acyl chain that I've boxed in a rectangle. So something like palmitic acid, which is 16 carbons. If I were to draw palmitic acid, I'll draw palmitic acid right here. Palmitic acid, these acyl chains would preferentially stack one with each other. In fact, that's how we depict the phospholipid, okay, a hydrophobic interaction between the acyl chain components. And if you have something completely saturated, like palmitic acid, you get optimal stacking. The acyl chains will stack very nicely. But what happens if you introduce monounsaturation or polyunsaturation, as in the case with linolenic acid? That stacking, that preferential interaction does not stack optimally. Okay, so the double bond actually introduces kinks. So that interaction now, okay, instead of something like this, where we would have nice interactions between the acyl chains by nonpolar interactions, okay, if they are saturated, once you introduce a monounsaturation or polyunsaturation point, the packing becomes bent or kinked. So you can imagine sardines where the acyl chains are packed very tightly to one another. Once you introduce that double bond into a fatty acid group, okay, here's fatty acid 1, here will be fatty acid 2. Now I add a double bond, I add another double bond, and now all of a sudden I have regions of the fatty acids due to the double bond that do not allow for that tightly knit packing. Okay, the acyl chain packing is disrupted by double bonds. The acyl chain packing is disrupted by unsaturation, whether it's monounsaturation or polyunsaturation. Okay, diunsaturation, triunsaturation. That packing results in a disruption because the double bonds will kink and distort out of the way. So they're no longer packed so nicely in your, for example, phospholipid bilayer by the presence of the double bonds. So double bonds really change the biophysical properties of the fatty acid, and because fatty acids are part of the phospholipid bilayer, they are a component of it, they will also change the biophysical property, they will change the properties of your membrane. So monounsaturated, diunsaturated, polyunsaturated fatty acid changes the properties of the membrane. So a couple of more things. These double bonds in the fatty acid usually are in the cis. They're usually cis double bonds. Very rarely you'll get trans double bonds, but for now, cis seems to be the best thermodynamic arrangement. Okay, cis double bonds. But you also have that actually adds for that packing if they're cis. If you have some other substituent there instead of the hydrogen, then probably you'll have trans, but usually phospholipids, when they pack and when the double bonds are added to the fatty acids, that double bond is usually in the cis form. Okay, cis double bonds is what we usually see here. Okay. One final thing here before I conclude this is an important property of fatty acids are what are known as a specific phase transition temperature, or TM. Okay, so fatty acids will pack, as we stated before. If this tail is the fatty acid tail, and phospholipids will have two fatty acid tails. What stabilizes these two fatty acids from interacting with each other is their hydrophobic interactions, or their nonpolar interactions. So a fatty acid will have a phase transition temperature. Okay, I'm only focusing on this region of the molecule, the long chain carboxylic acid end. In reality, a phospholipid and a phospholipid bilayer itself has its own TM. But right now, I'm only going to focus on the phase transition temperature of a fatty acid. Okay, so a fatty acid can exist in two forms. It can exist in a liquid crystalline form, and it's in an equilibrium with a gel form, crystalline versus gel. Okay, or you can call this the gel-sol transition, solution to gel or gel to solution. So some of these fatty acids actually exist as a gel. Some of them exist as a solution. All right, they are actually in an equilibrium with one another. So a little bit more detail, but the liquid crystalline form is called the L-beta, which stands for lamellar. So these can form lamellae. The gel form is called L-alpha. So the alpha-beta form is nothing more than the gel solution equilibrium. So taking a look at a simple fatty acid such as palmitic acid. So here are the 16 carbons of palmitic acid. They're going to pack really, really well. And if they pack really, really well, they actually can exist in the gel state. Okay? So here I have two molecules of palmitic acid, 16 and O, no double bonds, packing exceedingly well, like sardines in a sardine can. Okay? So what happens if you raise the temperature? If you raise the temperature, what happens is you have motion. Okay, these terminal methyl groups begin to rotate. These CH2 groups begin to rotate. The onset of molecular motion actually causes the packing to lose its viability. And now you have something that's more in the solution form. So a pure fatty acid actually has a phase transition temperature where it can go between the solution state and the gel state. So if we have a nice peak here, if we raise the temperature of our fatty acid, pure fatty acid, nothing more, nothing else, real fatty acids or real phospholipids have many different types of fatty acids, saturated and unsaturated, within them. But if we were to take a pure fatty acid and just raise its temperature And on the y-axis, we actually measure what's called Cp, which stands for heat capacity. If we put a pure fatty acid in, such as palmitic acid, and we raise the temperature, there's going to be one temperature where you'll have a nice, beautiful, sharp peak. Okay, and that temperature is called the phase transition temperature. That is the temperature where your heat capacity is maximal, and it is that temperature where you've undergone successfully the transition from a gel state to a solution state. Anything to the left of this thermogram, as we raise the temperature, is going to be the gel state. Anything to the right of this thermogram is going to be the solution state. Obviously, if you increase the temperature of something, it's going to become more solution. It facilitates going into water, or facilitates going into the solution state. So raising the temperature causes molecular motion, bonds begin to rotate, and the molecule just begins to jiggle in, jiggle out, and starts to dance, and it becomes more solution-like. Okay. Now, what happens when you introduce double bonds? Double bonds really distort the packing. They cause kinks in the packing, and the packing is suboptimal. So you don't get that nice sardines in the sardine can type of interaction with a double bond. So what happens when you have a double bond, when you introduce a point of monounsaturation, the results can be rather dramatic. Okay, so the same temperature on the x-axis, we'll raise it, we'll measure the heat capacity. Okay, you can actually see something that looks like this. All right, you actually see the melting temperature go down, but that's not really a legitimate depiction. But your peaks are no longer very sharp. You also get some broad peaks in there as well, because you have multiple different conformations that exist underneath this broad curve. So this is what happens if you add a phospholipid with a double bond or an unsaturation point. Okay, it takes less temperature for it to go to the solution state. If you have something that's completely saturated, it's going to take more temperature or more heat or more energy to initiate the formation of the solution state, or the L-beta configuration, the L-beta organization of these fatty acid molecules. So a lowering of the phase transition temperature happens dramatically. This is actually very dramatic when you have unsaturated and polyunsaturated fatty acids. So let's go back to our original problem here, and let's see if we can take these fatty acids. So first of all, given this, you should be able to draw the structure, but now you should also be able to rank the phase transition temperature, that specific temperature where these pure fatty acids would undergo gel to solution transition. All right, so let's the phase transition temperature, the T sub m, 1 being the lowest and then 5 being the highest. Okay, without looking at anything, without looking at any textbook or any encyclopedia, what would be the phase transition temperature from lowest to highest for palmitic acid, oleic acid, linoleic acid, linolenic acid, and finally arachidonic acid? How would we rank these? Okay, so remember, if it's saturated with hydrogens, a saturated fatty acid, generally it would have a very high phase transition temperature in going from L-beta to L-alpha, going from the gel state to the solution state. Gel state to the solution state. It has to do with the packing. So 0 double bonds here, I would predict this would have the highest amount of phase transition temperature. Okay, so these would be packed very nicely amongst each other. So that would be the highest. What would be the lowest phase transition temperature? The one that would be the lowest phase transition temperature would be the one that has the most double bonds. Okay, the one that has the most double bonds would have the lowest phase transition temperature. So that would be this one that has 4 double bonds. The next one would be the fatty acid that has 3 double bonds. Okay, so the one that has 3 double bonds would be this one, and then 2 double bonds would be next, and then the one that has 1 double bond would be the second to highest. or second to highest phase transition temperature, because you have more packing, less kinks with one double bond, as opposed to 4 double bonds where you have more kinks and more disruptions along the fatty acyl chain, so that the packing is not going to be so tight here as would be for here. Here you have 4 double bonds, here you have 1 double bond. If you actually look at the literature, the phase transition temperature for palmitic acid, I did look this up, is actually, this has a T sub M of 63.1 degrees. T sub M for oleic acid is 13.4 degrees. For linolenic acid or linoleic acid, the phase transition temperature is -9 degrees C. Okay, so adding 1 double bond actually reduces the phase transition temperature significantly, but we've also added 2 carbons, so it's really not a fair comparison. But going from a 1 double bond that's 18 carbons to 18 carbons and adding a single double bond, you're going from 13.4 degrees to -9 degrees. So that is a really, really steep drop just by adding 1 double bond at carbon number 12. How about keeping the carbons the same and adding a 3rd double bond? From -9 you go to -17 degrees, and then adding 2 more carbons relative to 18 carbons, adding 4 more carbons relative to palmitic acid. But having 20 carbons, 4 double bonds, this is -49.5 degrees C as its phase transition temperature. Okay, so that means at a Tm of -49.5 degrees, above that you get a solution state. So arachidonic acid is essentially a solution, unless you freeze it to like -50 or -60. Then you start getting this onset of the gel formation. Likewise here, linolenic acid, if you store it at -20 degrees, that's when it starts to form the gel. Anything above -17 degrees, it's going to be a solution. So even at 0 degrees or 4 degrees, linolenic acid is going to be in a solution state. Palmitic acid, you have to go below 63.1 degrees before it starts forming a gel. Above 63.1 degrees, it's going to start forming into a solution. So you can actually see, for example, at 37 degrees, or 42 degrees, you can actually see palmitic acid. If you put some palmitic acid in water, but you usually put it in a buffer, if you put it in water, or even if you put it in methanol, it just won't go into solution. Okay, in water it's going to be more gel, it's going to be very hydrated, but above 63.1 degrees, the temperature above its phase transition, you start getting the solution phase. All right, so just by cold turkey, just by getting this, you should be able to rank the phase transition temperatures of fatty acids without actually consulting the literature. One thing I do want to show you is I showed you the effect of the phase transition temperature as a result of double bonds. Okay, but here, what happens if you keep the carbon length the same but start adding double bonds one by one? Okay, you start seeing the addition of 1 double bond really significantly alters the phase transition temperature.